So let's get started. Today we're going to talk about very concretely how to go from on-shell diagrams and how to think about on-shell diagrams as really associated with some cells of the Grassmannian. And actually today the word positivity is not going to make an appearance. We're going to do all kinds of things and understand all sorts of things without yet seeing that the things that we're talking about are associated with boundaries of the positive part of the Grassmannian, the object that I talked about. After we get all this stuff under our belt, we'll sort of fairly easily be able to understand the word positivity and the notion of boundary, which is what we'll spend a lot of time talking about next time. Today we're just doing, we're just starting with a very practical exercise. We're trying to learn how to glue together on-shell diagrams. And let me remind you again that we're starting with our basic 3-point amplitudes. I won't write down the concrete formulas, but we have the supersymmetrically, we have the k equals 2 and the k equals 1 basic 3-particle amplitudes. And the most direct thing we'd like to do is learn how to glue them together to make pictures like this, some of which we drew last time, where gluing together means that everything in sight is on shell, and so when you have an internal line, you're supposed to integrate over the d squared lambda tilde d4 eta tilde, which does the helicity sum mod GL1 for the internal line. Okay, so that's what we'd like to do. So we're gluing these basic 3-particle objects together, and we'd like to learn how to integrate out the all the internal on-shell particles. And the practical difficulty is that if we do this in the most naive way, it's not so trivial to do these integrations because momentum conservation at all the vertices imposes quadratic constraints on the lambdas and the lambda tilde, so I can't just sort of trivially solve for the lambda and the lambda tilde with delta functions or something like that to do the integrations. Yes?
So is it possible to see these on-shell diagrams from a conventional iterative expansion?
They're related to things. We'll talk about this more next time. So these objects are called leading singularities in a more conventional way of thinking about things, and they're related to various cuts of integrands. So if you take some integrand, if you take an amplitude, the amplitude has some discontinuities. It has a branch cut structure at loop level. If you ask about the discontinuities across those branch cuts, they're computed by putting internal lines on shell. And so if you take as many discontinuities as you can, they're captured by diagrams where everything in sight is just on shell. Okay, so these objects, that's one of the reasons they look like loop diagrams, is that they actually arise from discontinuities of loop diagrams as well. Okay, so that's one. We'll have a little bit more to say about that when we actually talk about loops and the all-loop recursion relation. Okay, for now we're playing like we did last time. We're just playing with these things. And we're already rewarded last time by observing that, for example, a very simple looking operation like tacking on a bridge like this to some lower object is actually what BCFW is all about. Okay, so that we can actually represent all the terms in BCFW recursion relations by these on-shell diagrams. So BCFW looked like a trick, but it's a little bit more than a trick. All the pieces in BCFW are interpreted as some particular on-shell process. Okay, so that's one reason amongst many that it's interesting to try to interpret these things. But we'll have more to say about these leading singularities when we talk about loops more concretely. Okay, so this is the difficulty. But there's also a difficulty really sitting here right away in a representation of the 3-particle amplitude, that we had to be clever to notice that in this configuration, all the lambda tildes are parallel to each other. And in this configuration, all the lambdas are parallel to each other. Right? That's a consequence of momentum conservation. But we had to sort of observe that as a consequence of momentum conservation. But the Grassmannian representation of the 3-particle amplitudes, even if we didn't know about the whole fancy formula that I wrote down before, is just motivated as a way to make all of this as manifest as possible. Okay, so the Grassmannian representation for the white amplitude is some integral d cubed white mod GL1. And if I actually put in A, B, C here, okay, so it's really some d cubed white mod GL1 over these minors A, B, C. And I'm going to introduce a notation just so we don't keep writing it down over and over again. Just a delta of the whatever the C is. In this case, the matrix would be W, and lambda. This is a stand-in for all of lambda, lambda tilde, and eta tilde. And this whole object, this is just some notation. This is a stand-in for delta of C dot lambda tilde, delta of 2 times k, C dot lambda tilde, delta of C perp, 2 times n minus k, C perp dot lambda, and the delta for C dot eta tilde. Okay? So remember, this is all the way that the external data enters the problem is through this geometry that we've drawn a number of times, where I have my k-plane C, which contains lambda and is orthogonal to lambda tilde and eta tilde. Okay? But all of that, I'm just going to abbreviate in this delta of whatever the C is. In this case, my matrix, I'm just writing it. W is a matrix WA, WB, and WC. Okay, and so this formula makes completely manifest that the lambda tildes are parallel to each other, that the lambdas are parallel in this configuration. Okay, and the lambda tildes, and the whole thing ends up giving us the correct 3-particle amplitude. And similarly, for this guy, it's d squared d2 times 3, some black with ABC over some 2 by 2 minors AB, BC, and CA. And once again, mod GL2 now, delta of black and lambda. And so B would be, in this case, this matrix BA, 2 by 3 matrix BA, BB, and BC. Note something important about this. The W and the B, are naturally acted on by a GL1 for the W's and a GL2 for the B's. Okay, that's what we're modding out by. They're also naturally acted on by the little group for each column. Okay, so if I take column A goes to TA column A, then whatever the column is, white A is going to TA white A. The 8th black column is going to BA, TA times BA, and so on. Okay, so these GL1 and GL2s we're modding out by. This we're not modding out by. This is just the nice action of the little group on all the columns, and everything is covariant with respect to the nice action of this little group. Okay, so now what is the point? The point is that now we've trivialized momentum conservation. Now we can do all those internal integrations, d squared lambda tilde, because all the lambda tildes, and the lambdas occur as delta functions in these formulas. Okay, so we can just integrate over everybody and be left instead with an integral over all these w's and b's. Okay, so we're going to trade the integral over all the lambdas and lambda tildes of the internal ones, which we'll just do trivially, with, in the end, some integral over some set of w's and b's. But let's get an idea, just roughly what it is that we're getting. So each black vertex is imposing, so take any diagram like that one. Okay, every black vertex is imposing a condition BA lambda tilde A plus BB lambda tilde B plus BC lambda tilde C equals 0. Each white vertex is imposing instead. So this is WA lambda tilde A plus WB lambda tilde P plus WC lambda tilde C equals 0. Okay, that's from the delta C dot lambda tilde. It's the T dot C dot lambda tilde piece. We'll come back to the rest of them later. Okay, so as constraints on all the lambdas go, this is 2 times the number of black vertex constraints. This is 1 times the number of one vertex constraints. Okay, so that's the number of delta functions that we have. But we're going to integrate over all the intermediate lambda tildes, let's say. So just as far as the lambda tildes go, how many constraints are we going to end up having on the external lambda tildes? So the number of constraints on external lambda tildes is 2nb plus nw minus n internal. Okay? Now, not coincidentally, this number is also the k of the on-shell diagram. Where by k I mean the degree in the eta tildes, right? That's because every black vertex has weight 2 times, every black vertex has weight 2 times 4 in the eta tildes. Every white vertex has weight 1 times 4 in the eta tildes. But I'm integrating over the internal lines. Every one is a d4 eta tilde I. Okay, so the total weight that I have in the end is 4 times 2nb plus nw minus ni. Right? So I'm going to end up having a total of k constraints on the external lambda tildes, which is that k is the same as the super degree of this on-shell diagram. Okay, so whatever those constraints are, I mean, I just have a bunch of linear equations relating all the lambdas to each other. I'm just eliminating all the internal lambdas. This is going to end up giving me k relations between the external lambda tildes. Okay, so these relations take the form, and we'll be more concrete in a second to write it in a canonical way, but they take the form, there's some matrix C alpha A that will depend on all these white and black variables. Okay, but there's some C alpha A, lambda tilde A is equal to 0, okay, where alpha runs from 1 to k. And notice, because all I'm doing is just solving these linear equations, this is just some set of linear relations between the external data. And so I can do any k by k linear transformation on these guys that I like, and it's the same relations. Okay? So you see, just the act of gluing together the lambdas and the lambda, of gluing together these 3 particle amplitudes, has produced for me, out of the elementary white and black variables associated with the little g13s and g23s, it has produced for me a large k by n matrix, okay, where all I care about is the k by n matrix modulo GLK transformations. So from here, what I've done is produce from the black and white vertices, from black and white little g23s and g13s, I've produced some matrix C that lives in GKN. So I'm sort of parametrizing some part of GKN. There's various words for this, but this is the same as, especially in this sort of very invariant way of describing it, this is sometimes described as saying I'm amalgamating all these G13s and G23s together to produce something that lives inside GKN. Is that clear? So is it now clear where the Grassmannian is coming from? Okay, it's just this completely trivial thing that it arises from the fact that all the way back to the 3 particle amplitude, the fact that we have these linear dependencies in the 3 particle amplitudes, say the lambdas are parallel or the lambda tildes are parallel, is already telling us to associate those with small g13s and g23s, and in so doing, liberate us from imposing momentum conservation by hand. Once we do that and we glue all the objects together, then we're left with some relations. We have to integrate over a bunch of variables, but some relations that are associated with some point in the Grassmannian GKN.
So here when we say K equations, are you assuming the GL1 of the lambda tilde is?
We're not doing anything with the GL. No. We're just this has nothing to do with the dimensionality of the vector space on that guy. Okay? There's just a bunch of relations on the lambda tildes. All right. So let's summarize then. So what do we have? So we find that a given on-shell diagram, some given on-shell diagram, is equal to some integral. Let's call these forms for the white guys omega white and the forms of the black guys omega black. I actually have to mod out by the product over all the edges of the GL1 that touches the edges. Okay? Why do I have to do that? Because remember, that was part of my integration, right? Part of the internal integration was d squared lambda tilde modulo the GL1 that acts on the edges. And I told you, this is a very nice thing, that the GL1 on the edges is actually carried by these whites and blacks. Okay, so I can, instead of modding out by the GL1s when I integrate over the d squared lambda and d squared lambda tilde, I can leave the integral over lambda and lambda tilde free and mod out by the GL1 on the edges here. So that's, again, part of the magic, that you don't, all the nonlinearity you normally associate with phase-space integration is gone. Okay, and is, okay? And now I'm going to have, from the lambda tildes, we just figured it out, there's some delta 2 times k of this c, which depends on w and b dot lambda tilde. The same thing, delta 4 times k, I'll write it out once here, just eta tilde. And then it should not surprise you that if we go through exactly the same exercise and talk about the lambdas instead, then all the statements are about the perps. All the statements as we go along are about the perps. Already for the little 1, 3 and 2, 3, it's that the C perp is orthogonal to the lambda. And so what we'll get from the lambda part is another delta 2 times k C perp dot the same C perp dot lambda, 2 times n minus k. Okay, and so I can just to use my notation, this is now some integral omega, the product over the white and black, omega white, omega black, mod GL1 on the edges, times this delta of C of W and B, and lambda. Okay, so all of the dependence on the external data has gone into those delta functions. Okay, now let's get a quick idea for the actual number of integration variables we have that you want to sort of associate with the dimensionality of this configuration in C, right? So I'm sort of covering maybe not all of GKN. If I have a very few variables, maybe I'm covering only some part of GKN. I want to have some idea what's the dimensionality, or maybe I have a whole stack of variables, right? I want to have some idea how many variables am I integrating. So I'm going to call for the moment a notion of a dimension of this cell, which is just the obvious one. Like with every vertex, I have 2 degrees of freedom from the G13 and the G23, right? The dimension of G13 and G23 is 2. So I have 2 degrees of freedom from each one. So the dimensionality of C should be 2 times the number of vertices minus the number of internal edges, right? All the ones that I'm integrating over. If I'm drawing trivalent graphs, I also have that 3n vertex is equal to twice the number of internal edges plus the number of external guys, n. And therefore, the dimensionality of C is also given by n, n vertex minus ni plus n, which is actually the number of faces of the graph minus 1, where the number of faces includes the boundary faces. So from now on, at least for this lecture, I'll draw the diagrams often like this inside a disk. So I might draw something like this. Okay, so in this picture, there are 1, 2, 3, 4, 5, 6, 7 faces. Okay, and so the dimensionality of this cell would be 7 minus 1. So NF here is 7, and so the dimensionality of this associated cell would be 7 minus 1 equals 6. Okay? All right. So that's just sort of abstractly what it is that we are doing. And notice that you could have all kinds of problems. I mean, all sorts of questions already. For example, if I draw a horrendously complicated diagram, obviously this dimension, I could have a gazillion faces inside it. I can draw a horrendously complicated diagram with a gazillion faces inside it. The dimensionality of the Grassmannian is bounded from above. It was k times n minus k, right? So there is some match we have to make between so we can have way more variables naively than the dimensionality of the space. So that's already some indication that there are going to be some diagrams that are sort of minimal and are reduced, and other diagrams are going to have all sorts of irrelevant or naively irrelevant, but actually physically important, ultimately decorations on top of it. So we're going to be getting there. It's going to be notion of reduced and unreduced diagram. But even for unreduced diagrams, this counts the number of integrations there are, just trivially, just how many variables there are associated with the graph. Okay, so next what we want to do is give a more practical way of actually doing this computation. It's just a particular way of doing these various gauge fixings so that everything is as clear and simple as possible. And this is going to lead us to the notion of boundary measurements. Okay, so and what this is going to do is going to give us a particular presentation of our matrix. Okay, so recall that if we have something in GKN, let's say something in G36, okay, then naively, well, I just have 6 three-dimensional column vectors, but it's useful often to gauge fix in some way. So we can gauge fix by choosing any 3 of the columns and just declaring that they're the identity matrix. Okay, so we can always gauge fix the GL3 by saying, let's say columns 1, 2, 3. They don't have to be well. Let's say it looks like 1, 0, 0. Something, 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 0, 1, 0, 0, 0, 1, and then these are generic. Okay? And of course, this is just a coordinate choice. I can choose any other set of coordinates that I like. But this is just, but you know that if you're doing any practical computations, you'll always end up choosing a gauge and doing something in this gauge. So we're now going to give a picture that's going to actually give us a representation of the matrix in any gauge that you like of this sort. Okay? And the idea is that whoever you're gauge fixing to the identity, you're going to represent by adding arrows to the diagram. So we don't have arrows on the diagram to begin with, but we're going to now decorate the diagram with arrows, and whoever the k guys are that are gauge fixed to the identity, so whoever these k guys are will be represented by incoming arrows, and the remaining n minus k guys are going to be represented with outgoing arrows. Okay, and we can think of each row of this matrix as kind of telling us a way to represent these sinks. I can think of like the incoming guys as sources. the outgoing guys as sinks, and I want to give you all the non-zero rows in this matrix. It means that I want to tell you how do I write 2 in this row as a combination of, so 1 will be represented as a combination of 2 plus 5 plus 6. Okay, 3 will be represented as a combination of 2 plus 5 plus 6, and so on. So that's how I want to read those rows of the matrix. Okay, so in order to do that, so we're going to build an oriented diagram, and this is going to be associated with the notion of a perfect orientation. And the k equals, so that means that every white vertex in the picture should have the property that there's 1 incoming line and 2 outgoing lines. And every black vertex should have the opposite property. Okay. Should have 2 incoming and 1 outgoing. Okay, does this make sense? So if you wanted to imagine that we're just playing this game literally with one of these vertices, you might say that you're gauge fixing this one to be 1, and then I'd have these other 2. Right? Or here, I would gauge fix these 2 to be the identity, and I'd have the 2 variables associated with that with that final leg. Okay. Okay. And so you have to draw your diagram. You have to make some choice for who you want to be sources and sinks. You will end up having to have exactly k incoming arrows and n minus k outgoing arrows. If your diagram has whatever k your diagram has, you've got to make sure that k of them are in and n minus k are out. And then it's slightly non-trivial, but it's pretty easy to convince yourself this is true, that you can always give a perfect orientation to any graph. Okay? Provided the following is true, that, you can always give a perfect orientation to any graph, provided that there are no subgraphs for which the k of that subgraph, if you just looked on the little subgraph, if the k is less than or equal to 0, or greater than or equal to the number of legs sticking out of it, okay, then you can't perfectly orient the graph. But those are exactly the situations where, as physicists, we would assign those graphs 0. Okay, so we can't, in that case, we would have either too few or too many Grassmann integrations, and we just get 0 from that answer. Okay, so we have to have k bounded between 0 and n, and if you have any subgraph for which k is less than 0 or bigger than the number of lines entering the subgraph, then you might not be able to perfectly orient the graph. But those are exactly the graphs that we don't care about. We're just setting all those things to a 0. Okay, so everything that we care about, we can give a perfect orientation to. All right. And now I'm going to assign sort of concrete variables to these. I'm going to assign concrete variables to these guys. So if this is A, B, and C, and A, B, and C, my W matrix, which remember I should officially be gauge fixing, so it's only has 2 degrees of freedom. Okay, but I'm actually going to be very slightly sneaky here, and I'm going to write it in the following way: alpha A inverse, negative alpha B, negative alpha C. And similarly, this black 2x3 matrix, I'm going to write as alpha A inverse 0, 0 alpha B inverse, negative alpha C, negative alpha C. I'll say why I'm doing it. So each one of these has 1 extra degree of freedom compared to what they should have, right? Naively, each one should have 2 degrees of freedom. I'm slightly artificially adding 1 extra degree of freedom for each one, although it's not artificial. We'll see why I'm doing it in a moment. It has everything to do with those GL1s for the edges that we care about. But let's just see what we're doing then. So this white is imposing the equation lambda tilde A is equal to alpha A, and I put the minus signs there. Alpha B lambda tilde B plus alpha C lambda tilde C. So the white is imposing these equations, and the black is imposing these equations, lambda tilde A is alpha A, alpha C, lambda tilde C, and lambda tilde B is alpha B, alpha C, lambda tilde C. Okay? Now, I introduced these extra GL1, so each guy has one extra degree of freedom, which I should be gauge fixing, right? That degree of freedom I can think of as a GL1 associated with the vertex. It's very slightly interesting because we've gone from the GL1s that we care about on the edges. Now what I've done is introduce a bunch of extra GL1s on each vertex. Okay, so for example, I can use the GL1 on the vertex to set alpha A to 1 if I like, or to do anything I want with these guys. But I'm introducing some extra GL1 associated with the vertex. With the black vertex and the white vertex. Okay. So now let's see what the point of all of this is. Let's do our first exercise, and then we'll see. And once you see how this works, I can just write down the answer. In general, it's very obvious. Oops. All right, so let's look at our first maybe slightly interesting on-shell diagram. Let's look at this diagram. Okay, so that's the diagram, and now I'm going to give a perfect orientation to the diagram. Okay, so my perfect orientation is to do this. So you see, it was not unique here. I could have had 2 come in and 3 go out. I chose to write it like this. Okay, so now let's look at what these equations are that we just talked about. Okay, so on this side, I have a variable here. I'll call it alpha 1, alpha 4, and let's say alpha intermediate on this side. On this side, I have alpha 2, alpha 3, and this is not the same as that. This is some other variable. Let me for now call it beta intermediate. Different variable on this side. Is that clear? Right? So let's now write down the formula. So from this side, this white vertex tells me that lambda tilde 1 is equal to alpha 1 times alpha 4 lambda tilde 4 plus alpha I lambda tilde I. That was a formula from the white vertex. From this side, I learned that lambda tilde I, so this is from the white vertex. From the black vertex, I learned that lambda tilde I is beta I alpha 2 lambda tilde 2, and that lambda tilde 3 is alpha 3 alpha 2 lambda tilde 2. Okay, so I've solved for lambda tilde I rather trivially here, so let me shove it back in there, and now I have the relations between the external data that I'm after, right? I've gotten rid of lambda tilde I, and I'm left with the relations solve for lambda tilde I, and I'm left with the relations lambda tilde 1 is equal to alpha 1 alpha 4 plus alpha I beta I in this nice combination together times alpha 2 lambda tilde 2. And meanwhile, lambda tilde 3 is just equal to alpha 3 alpha 2 lambda tilde 2. Okay. Now let's, yeah. Oh, I'm sorry. What happened to? Oh, I'm sorry. Lambda tilde 4. Thank you. Thanks, you. Now, notice something about this combination. The combination that occurs there now has no weight under the intermediate guy, right? that's good. So when I'm doing, when I'm really literating d squared lambda tilde mod GL1, there really was an alpha I and a beta I, but I have to integrating over them mod GL1. And this combination, alpha I, beta I, is exactly the GL1 invariant combination. Okay? So when I glue these things together, what I get, I have these alpha variables on the outside, but all the variables that I get on the inside will also be charged under the GL1. All the GL1 of the edges is gone. They're just charged into the GL1 of the vertices. And they're charged into the GL1 of the vertices like you're used to as a physicist, as if they had equal and opposite charges. If it's an arrow going from one side to another, it's like lattice gauge theory, right? Arrow from one side to another, it has plus charge under this GL1 and minus charge under the other one that it's going into. Okay? Yeah.
When you say it's like lattice gauge theory, is there anything deeper going on?
Not at the moment. Maybe in the second week of December we'll have something to something along these lines. So let's go back to the picture. So you see, alpha and beta, they started off life attached to these vertices, but actually we really get the combination alpha and beta that's associated with the edge. So let me clean up this picture a little bit. And now I can really imagine that all of these variables, the ones on the outside, whether I call it the vertex or the edge, it doesn't matter much. Let me now just say that they're associated with the edges, even the way I drew it, right? So, and let me call this composite thing, I don't know, let me call it gamma for now, okay? Okay? So now this is really my picture. And now what I want to know is how can I read off this relation between the lambda tildes without doing this work of, it wasn't much work in this case, but doing this work of solving for the intermediate lambda tilde and shoving it in. And the answer is simply the following. There's a formula that says lambda tilde 1 is equal to some combination of the, so this is a source that's going to be some combination of the sinks. So in order to see what it is times, sorry, what did I do? Sorry, this is out. Okay, so it's going to be something times lambda tilde 2, which is a sink, and something times lambda tilde 4. Okay, and this something is just, for example, for lambda tilde 2, what did I get? For lambda tilde 2, I got this, oh, sorry, there's an alpha 1 in front of the whole thing. Sorry. Oh, sorry, I do have, there's an alpha 1 in front of this. Okay, so the thing that was in front of lambda 2 was alpha 1 gamma alpha 2. But that's exactly what I would get if I took this path from 1 to 2, just following the arrows. Similarly, for lambda tilde 4, I got alpha 1 times alpha 4. Well, that's the path that I would get following the arrows between 1 and 4. What about the formula for lambda tilde 3? This is, in general, something times lambda tilde 2 plus something times lambda tilde 4, again. But now, what is this to 2? Again, I just have to follow the arrows to 2. So that's, I get alpha 3 times alpha 2. And there's nothing that goes to 4. So that coefficient is 0. Okay, and in fact, that's the completely general formula. So this is what's called the boundary measurement. I think the word is sort of meant to signify, again, you have a picture, you're trying to build this matrix on the outside, so you're sending in some, you have some sources and some sinks, And this is just giving you a relationship between the external data that comes from all this inside of the graph. And so if I have the A's are my k sources, and my I's are the n minus k sinks, then I get a formula that just says lambda tilde A plus CAI lambda tilde I equals 0, where negative CAI is equal to the sum over all the paths gamma from A to I, the product over all the edges in the gamma of alpha edge. And you could have situations where you have paths that wind around, in which case you have to sum the infinite sum and write down the geometric series. Okay, so you have a formula with a denominator if you did that. Okay. This is actually, it's very easy to prove, and it's very easy to prove sort of inductively, basically because no matter how complicated the graph is, this also gives you a formula for a lambda or a lambda tilde deep inside the graph. Okay, and so we can just use that inductively to build up the whole picture. So let me give you an example, a slightly more complicated example then, just so we see how it can work. So let's look at our favorite square here. And let me do a different perfect orientation. Let's say 1 and 2 are going to be incoming, and I'll orient it like this. Okay, and I'll call these alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, and alpha 8. Okay, so I have naively 8 variables here. And so let's write down the formula. So what is negative C13? Okay, I just have to draw all the paths that I can between 1 and 3. Notice last time we talked about this left-right permutation path. This has nothing to do with that. Okay, we'll come back to that in a second. This is just paths following the arrows in the orientation, nothing else. Okay. Okay, so here I can go from 1 to 3. For instance, there's only one way to go from 1 to 3. I can go from here, there, there, there. Okay? So negative C13 would be alpha 1, alpha 5, alpha 6, alpha 3. So let's look at C14. So C14 is a little more interesting because one way I can go from 1 to 4 is like this. So one contribution is alpha 1, alpha 8, alpha 4. But I can also go around, maybe I should use a different color. Well, I can also go around like here, there, 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 and there. So I have to add plus alpha 1, alpha 5, alpha 6, alpha 7, alpha 4. Okay, and you can, negative C23 is alpha 2, alpha 6, alpha 3, and negative C24 is alpha 2, alpha 6, alpha 7, alpha 4. And so concretely with this picture, we've associated our 2x4 matrix. So with this picture, we have associated a big matrix C, which is 1, 2, 3, 4. We've gauge fixed 1, 0, 1, 2 to 0, 1, 0, 0, 1. And we have C13, C14, C23, and C24. Okay, any questions about this? Yeah.
Can you say again where the alphas came
The alphas were there. The alphas from the very beginning were just the variables that were representing the 3-particle amplitudes. Okay? So remember, we're representing each one of the 3-particle amplitude as an integral of these little auxiliary Grassmannians, these little white and black vertices. Why were we doing that? Because it makes momentum conservation obvious, right? And even the peculiarities of 3-particle momentum conservation obvious. Once we do that and we represent all the 3-particle amplitudes in that way, when we write everything down, integrating the on-shell phase space becomes trivial, and we're left with an integral over the parameters associated with the white and black vertices, which in the meanwhile, all the delta functions associated with the external kinematics have grouped the white and black vertices together, variables together, to giving us some k by n matrix. Okay? So we're getting an integral of some measure that looks like kind of d alpha over alpha, roughly, for everyone. Okay? With some interesting matrix that depends on these alphas in some sort of intricate way, interacting with the external data via our delta of c and lambda. Okay? So that's all we're doing. That is all we're doing. And you don't have to do it in this. You can just go and brutally gauge fix any way you want and carry out. I mean, once you do this Grassmannian representation, anything you'll do will get some k by n matrix out of it. Okay? Here, I'm just representing it slightly more nicely by leaving this GL1 freedom associated with every vertex. I did that in order to allow all the variables involved to have nice weights under the internal GL1s that I'm modding out by. Okay, and then and after I did that, I go from having this sort of whole stack, if you like, 3 times the number of vertices, variables, to having fewer variables, but which are naturally associated with the edges of the graph. And there's still the GL1 redundancy that I need to mod out by, associated with each vertex. So now I have a picture that kind of looks like a lattice gauge theory picture. I have a graph with a bunch of GL1s and all the vertices, a bunch of links that are charged under the vertices that they touch, and I've given you a way to build concretely a k by n matrix associated with it. Okay, and now as you can see already in this example, I don't actually have 8 different variables here, right? These variables are occurring in very specific combinations here. And why are they occurring in very specific combinations? Because the entire thing has got to be invariant under GL1 to the 4th, GL1 associated with every vertex. Okay, so that's actually our next item of business. But before we do that, let me just say what we've seen very concretely how to do is now write down a formula that looks like a given on-shell diagram is some integral d alpha over alpha associated with the edges mod the product over all the vertices of a GL1 associated with each vertex. And I've told you how to build a matrix out of all these alphas, which is going to interact with the external data. Okay, so that's where we are now. So once again, let's see how many variables do I actually have. Well, in this picture, how would you count? So let's say we go back to this picture. What's the GL1 invariant content of this picture? The GL1 on all the vertices. Okay, well, what are the GL1 invariants? What are you used to when you think about plaquettes in lattice gauge theory? How do you make objects that are invariant under the GL1s that act on all the vertices? You look at fluxes, right? So the things that are GL1 invariant are like products. I'm going to by convention say I'm writing the product clockwise. So it'll look like alpha 2, alpha 5 inverse, alpha 1 inverse. Okay, so I'm going to use that. I'm going to define the invariant content is associated with the faces of this graph. That's good. If you remember, we just saw from counting that the number of variables was equal to the number of faces of the graph. -1. We'll come to the -1 in a second, okay? But all of these guys are actually associated with a face variable. I could call it f1. But f1 would be alpha 2, alpha 5 inverse, alpha 1 inverse. Is that clear? Yeah.
Don't you have a separate GL1 for each?
I have a separate GL1 for each vertex. And so I have this.
You also need GL1 for all the vertices.
Sorry?
GL1, not the little group.
That's right. That's just a GL1 for all the vertices. Exactly. That's right. Yeah. Yeah. It's GL1 for all these internal vertices. Exactly. Yeah. So I have this face variable, f1. I have this face variable, which is like alpha 3 inverse, alpha 6 inverse, alpha 2 inverse. F3 is alpha 3, alpha 7 inverse, alpha 4 inverse. F4 is alpha 4, alpha 8, alpha 1. And F0 is negative alpha 5, alpha 6, alpha 7. Oh, sorry. Now, it's just it's a dumb convention. We're not talking about positivity today at all. But by convention, we put a minus sign in front of those variables. It's not relevant now, but it'll be useful later. Okay, so those are the invariant variables. So really, the variable, even though it's convenient, and there's nothing wrong with it, and in fact, there's even less wrong with drawing one of these things down and just gauge fixing the GL1 willy-nilly, however you like. For example, I can gauge fix alpha 1, alpha 2, alpha 3, and alpha 4 to 1. Done. Okay, and I'm left with 4 variables, which is the correct number of variables. Okay, or I could do it any other way I like. So I can mod out by the GL1 any way I like. I can gauge fix any way I like. But these face variables are the invariant content. And you'll see just by definition, so if I draw it again here, F1, F2, F3, F4, and F0, the product of all the face variables is actually equal to 1. Okay? And that's why I don't actually have 5 independent variables here. I only have 4 of them, because the product is equal to 1. Yes? Oh, I'm sorry. I probably didn't write all of them down. So it should be alpha 5, alpha 6, alpha 7, alpha 8. Sorry. Alpha 8 inverse. Thank you. Thanks, you. Okay? All right. Now, in terms of the face variables, what are the boundary measurements? How do we say this word in terms of face variables? Now it's the Anschauer diagram is equal to the integral now over this is over the product of all the edges. This is all the product of all the faces, df over f, just modulo a single global GL1, which is this product of f equals 1 business. Okay, so that just means I can just throw out any one of them, okay, or set any one of them equal to the product of the rest. Okay, delta of c that now depends on the face variables and lambda. And what is the boundary measurement formula for c given face variables? It's exactly the same thing, just that cai is equal to the sum over all the paths gamma from a to I, the product over the clockwise closure of gamma of negative, because I put my dumb minus sign in front of everything, negative the face variables. So what is the clockwise closure? For example, in this picture, if I go back to what I did, so let's say in this case, Okay, so beforehand, I was saying that I would get a contribution from this path, say, for C13, right? C13 would have a contribution from here, which was the product of all the edge variables. Now, what am I going to have instead of the product of all the edge variables? I'm going to have the product of all the face variables to this side of the path. Okay, so that's the invariant way of saying the answer for the boundary measurement in terms of the face variables. Okay, any questions about this? So we're going to be spending quite a bit of time inside, I mean, the next 2 lectures probably, inside the Grassmannian. So I want to just pause for a second to say, everything about the external world is now is like a window looking into what's going on in the Grassmannian. All the dependence on the external data is just in this dumb factor, delta c dot lambda. All the excitement about what the on-shell diagram is, what's going on, is now about what this matrix looks like. So we're making a particular kind of matrix out of this. We're not making, in this case, we happen to have made the most general 2x4 matrix. But for more interesting on-shell diagrams, we're not going to make the most general matrix. We're going to have to learn what these matrices look like. What does this configuration, I have a configuration of n k-dimensional vectors. There's something special about what that configuration looks like, even before we talk about positivity that we'll get to later. Okay? So we're going to be thinking a lot about what these things look like inside the Grassmannian, and the external world is going to come in at the very end in this delta c dot, in this delta of c and lambda to sort of extract, is look at what's going on in the Grassmannian and transmit into some function of the external data in the end. Okay? All right. So now let's start talking about equivalences, equivalence relations between on-shell diagrams. So we already saw this sort of intuitively last time, so I want to say it a little bit more. So last time, for example, we said that if I have, the simplest thing was the merge-unmerge operation. That if I had this graph and that graph, that what it meant as far as the external data was concerned was that just all the lambdas are parallel. All 4 lambdas are parallel. And so it doesn't matter which way you represent it. It's going to make all 4 lambdas parallel. So that was our intuitive way of concluding that these things have to be the same, right? Well, here we can also very trivially see that they're the same in the sense that these 2 pictures, whatever else is going on in the graph, these 2 pictures are going to generate exactly the same k by n matrix, exactly the same point in the Grassmannian. If I say it invariantly in terms of the face variables, if I had some face variables f1, f2, f3, f4, then I have to have some f1 prime, f2 prime, f3 prime, f4 prime. So the claim that they're the same is that there's some sort of map between f1, f2, f3, f4, and f1 prime, f2 prime, f3 prime, f4 prime that makes the points in the Grassmannian the same, and the map here is totally trivial. They're just the same. Nothing happens to them, as is sort of obvious from the picture. Okay, so they're just. Okay. So these 2 points, anything you put them anywhere inside an on-shell diagram, they'll produce the same point in the Grassmannian. The interesting one is the square move. And I know I promised you guys a problem set today, but I want to actually do today's lecture and Thursday's lecture so that you can have a meaty Grassmannian problem set. And so you'll prove this on your problem set, because it won't be super illuminating if I just do the algebra for you in real time. I'll tell you the answer. But this is really the exciting move. If you give me this square, and let me represent it invariantly in terms of the face variables. Okay, this and the other square where I color the vertices oppositely. Okay, in order to represent the same point in the Grassmannian, now I do have to change the variables. Okay, but this is the change. So I have to have, let me see if I can write it here. F naught prime is equal to 1 over F naught. F2 prime is equal to F2 times 1 plus F naught. F1 prime is equal to F1 over 1 plus F naught inverse. F3 prime is F3 over 1 plus F naught inverse. And F4 prime is equal to F4 times 1 plus F naught. So you see, this is a more exciting change. This is a more non-trivial change. But if you want to go, and this can be anywhere inside a big graph, right? So whatever's going on, you can have this square inside any graph you like. And you have to, in order to keep the point in the Grassmannian fix, you can check this already for G24, right? Just for this picture. You can build one point, you can build the other point, and just ask you can compute the boundary measurement from the two picture, ask how the edge variables have to be related to each other in order for the point to be the same, compute the face variables that go along with the edge variables, or do it the other way directly in terms of the face variables, and then just ask what does it take for the ratio of the 2 by 2 minors of one matrix to equal the ratio of 2 by 2 minors of the other matrix. That's what it means for you to have the same point in the Grassmannian. And this is what you'll find. You'll find this interesting, non-trivial change. But it's possible, and most importantly, remember the measure that we have in all these on-cell diagrams is the product of these d face over face variables. Crucially, product of df over df is equal to, actually with the minus sign, the product of df prime over f prime. So the measure is actually invariant. The point in the Grassmannian is the same, and the measure is the same. Up to sign. We're not going to be so. I'll have a little bit to say about overall signs at the very end. So I hope it's clear why the last thing is true, right? Because all of these things are just proportional up to these factors of f naught. And so if I wedge all the d logs of the f's, I get the same as the wedge of all the d logs of the f primes. This might be this might be, if it's inside some big complicated graph, I'll have all 5 of these f's will matter. If it's literally for G24, there's a constraint that the product of all the f's is equal to 1, but regardless, the wedge product is the same for both sides, whether it's all 5 of them or just 4. Yes?
So this minus sign is particularly these plots diagrams, right?
Sorry?
This minus sign comes for particularly these, right? Because it's not consistent with the earlier one where they were identical.
It's not consistent with which ones whether they're identical.
The T and S channel looking ones with the 2 black vertices, there you said that the f primes were the same as the f's. So this isn't a general formula. What's the...
Yeah, I'll have something to say about the overall sign later.
But,
okay,
but
that's
yes,
yeah,
but
right.
in general,
Yeah.
it's always going to, the equivalence is always going to have some sign factor.
That's right. The equivalence has some sign factor, but if you define things properly, when we talk about positivity, I'll say something about the signs. So don't worry about the signs. Don't worry about the signs right now. Yes.
So if I do 2 square moves, I should
Yeah. That's right. That's right. So if you square this, you'll come back to itself.
Maybe I'm making a trivial error, but it seems like if you take f1 factor, you will have a denominator with 1 plus f.
Yeah. So you'll have to do it. So that's what you're going to do. That's what you'll do on your problem set. If you do this twice, it'll come back to itself. Okay. It's not trivial. Okay, so so much for these so much for these moves, and these are the only equivalence relations. Okay, for literally equivalence relations, these are the only equivalence relations. The only interesting equivalence relations we're going to need. Okay, however, now let's come to this notion of reduction. And I could actually start with a simple example, but let me actually start with a slightly more complicated example. So let's say I had something like this. But now I sort of attach it to another box. Okay? So, I mean, you might already be nervous because this thing has, we already know that the box had all the variables you need, 4 variables. That's the dimension of G24. This is already more than the number, the dimension of G24, so what is going on? Well, in this case, let me do a square move on this guy. So if I recolor the squares here like that, okay, and so now I can do a sort of a merge unmerge on the merge unmerge on this middle guy, and so you see I'm going to get a bubble on the inside. And actually I can keep going and actually get more than one bubble in this picture, but this already just to give you an idea that I can get if I do a merge unmerge here, then I can have something that looks like a bubble on the inside. Okay? All right, so what do we do with these bubbles? So let's say I had this. So let's say in my on-shell diagram to begin with, I had a bubble, and I'm going to imagine that if this is inside a diagram, it doesn't matter what else is going on, but I have some perfect orientation here just for fun. So alpha and beta. So what is going on as far as anything is concerned as far as anything is concerned here, whatever's coming in here is going to go around this way plus going around that way, right? And so this thing is completely equivalent as if there was no bubble there, but I replaced alpha and beta with a single variable alpha plus beta. See, as far as the point in the Grassmannian is concerned, this thing is giving me exactly the same point as if I didn't have any bubble there, but my new alpha variable associated with this line was alpha plus beta. Is that clear? So you see how stupid these bubbles are, right? They're not actually giving me really new points in the Grassmannian, right? They're sort of covering yeah. So it looks like it naively looks like I would sort of increase the dimension of the thing that I'm covering by 2, but I'm really only increasing it by 1 because the point of the Grassmannian that I get only depends on alpha and beta. If you say this in the language of the face variables, you can also work it out very easily. You'll do this on your problem set as well. If I say it more invariantly, if I have f1, f0, and f2, then this is exactly the same as getting rid of the f1 and replacing f1 with f1 prime, which is f1 times 1 plus f0, and f2 prime, f2 over 1 plus f0, over 1 plus f0 inverse. And once again, the crucial thing is that the form is invariant. So if I look at, I had to begin with df0 over f0, df1 over f1, df2 over f2. This is df naught over f naught, df1 prime over f1 prime, df2 prime over f2 prime. For exactly the same reason, right? d log f1 prime is the same as d log f1 when on the support of anything that I wedge into df naught. d log f2 prime is the same as d log f2. Okay, so wedge of d log f naught, d log f1 prime, d log f2 prime is the same as wedge of d log f1, f naught, d log f1, d log f2. So that's what's beautiful about this reduction, is that I might have a very complicated diagram. I might think it's painting some ridiculously high-dimensional part of the Grassmannian, but I can systematically go I might have to go do square moves on it, blah, blah, but the second I produce a bubble, I say, aha, bubble gone, right? And I pull it out of the form. I pull the d log f naught out of the form. Of course, I don't totally forget about the variable. I have to modify the remaining ones according to this rule, right? But then I just keep on going. And so by the time I'm done, no matter how complicated the diagram is, I strip out of it a stack of d log of the bubble variables multiplied by something that I can't do that for anymore, and which we then call reduced. Okay? So I've given you a pragmatic definition of a reduced graph. We'll give a more I've given you a simple-minded definition of a reduced graph, one that any number of square moves and merge on merge will never produce a bubble for you. Okay? And any bubble that you see, you can just remove in this way. It might not be obvious that there's a bubble in the diagram. Like the picture that we started off to begin with does not obviously have a bubble in it. So I will tell you, I'll tell you next time how we can stare at a picture and figure out if it's reduced or not reduced and so on. Okay? But so we can tell that that picture is not reduced, and so we have to go hunting for bubbles. Okay? But the big picture point is that you might naively think on-shell diagrams are horrendously complicated, just like Feynman diagrams are horrendously complicated, right? And I could have at 100 loops, I could have a gigantic, factorially enormous number of different diagrams. It's not true. The on-shell diagrams are much, much more constrained than that. And no matter how complicated the picture is, they have to fit in the Grassmannian. Okay? And that means that no matter how complicated it is, you can strip off a stack of d-logs of bubble variables until you finally find something, a finite number of objects that are associated with the reduced graphs. And furthermore, even the finite objects that you have left are not as many independent ones as you might have thought, because they're still related by the merge, unmerge, and the square moves. Okay? So we're going to have to figure out, A, what is already for reduced graph, what is the invariant content of the graph? How do we decide whether two graphs are the same or not? We already saw a clue of that last time, just playing by defining this permutation associated with the picture. So we took these left-right paths through the picture, and that permutation was at least an invariant that was invariant under the merge, unmerge, and the square moves. So you could at least use it to check whether two graphs have a chance of being related to each other by merge, unmerge, and square moves. The remarkable statement is that when the graphs are reduced, in fact, it's complete. Every graph, all the reduced graphs can be related to each other by the merge, unmerge, and the square moves. And so this permutation is in fact a completely invariant labeling of what the reduced on-shell diagrams are. Okay, so if you give me the permutation, there's one invariant function that you can associate with it. There's one point, or there's one sort of cell in the Grassmannian, and associated with that, there's one kind of on-shell function that you can associate with it.
Maybe I'm making a mistake.
Yes.
Are you saying that this bubble removing move?
Yes.
It looks like it doesn't preserve the permutation that you're getting. Yeah.
Absolutely not. That's actually one of the bad things about it, right? Absolutely. So that's why if you don't have a reduced graph, if you just read off the permutation from the reduced graph, you're not necessarily going to know where you're going to end up. Okay, so the permutation is not preserved under bubble reduction. Okay? It's not preserved under bubble reduction. But next time we will understand what you have to do. Okay, yeah, I think that yes. There was another question. Yes.
Why is it you take two different
I think that's sort of completely clear from where it came from, right? That's totally clear from where it came from, because all we're doing in giving perfect orientations is giving some particular way of solving the stack of equations that we're getting from all of the black and white vertices, okay? So every way of solving those equations will be equivalent to every other way by some k by k linear transformation. Okay, so that's why it's obvious from this picture. That's why it's completely obvious from the amalgamation picture that you're making the same point in the Grassmannian. You're just finding different practical ways of representing that point in the Grassmannian. So that's the advantage of this amalgamation picture. And the amalgamation picture will also make positivity obvious when we start talking about positivity, but we haven't quite gotten there yet. Okay, the next topic I wanted to talk about, I think I should not get started on, because I don't want to rush through it. So why don't we just leave it at that, and next time we'll come back to this picture of, we'll go back to drawing one of our favorite BCFW terms that last time we associated with these cool permutations, and I'll tell you what these permutations mean. That these permutations capture something about the geometry of the point of the configuration of vectors that you get in the Grassmannian. And after we see that picture, you can ask various natural questions, like you know that already from ancient times, you probably know from like childhood, there's a very pretty way of taking any permutation and ordinary permutation and breaking it up into a product of adjacent transpositions. And that picture is actually associated with scattering processes in quantum field theory. That's way too fancy, but you've all seen this. How do you break up an ordinary permutation into a product of a bunch of adjacent transpositions? Let's say I have, I don't know, 1 to 4, 2 to 3, 3 to 2, 4 to 1. Then I would just write down 1, 2, 3, 4. And 1, 2, 3, 4. And sorry, I would just write them 1, 2, 3, 4, 1, 2, 3, 4, and I'd just draw the permutation. 1 to 4, 2 to 3, 3 to 2. Oh, bad picture. 3 to 2, and 4 to 1. Okay. Very hard to avoid bad crossings in this picture. Anyway, this, if the lines were straight, which they're not, you can think of as just a picture of particle scattering in one dimension of space and one dimension of time. Okay, so this is time, and this is space. And you just think of this as particles moving along a line and colliding one pair at a time, right? And if you don't have any particle creation or destruction, if your only basic scattering process is 2 to 2, then okay, this picture also tells you how to represent the product, the permutation as a product of adjacent transposition. Every interaction that you run into as you move up in time is just represented as one of the transpositions. Okay, and of course there's many ways of breaking up an adjacent transposition. There's many ways of breaking a permutation into a product of adjacent transpositions, and correspondingly there's many ways of drawing this picture. I can move these lines around. There's nothing invariant about the ordering in which all the various events happen, so long as the final permutation ends up being the same. So that's a very, very old connection in physics between permutations and scattering. And in fact, for integrable systems, if you really want the only thing to matter to be the permutation and nothing else, you have to put a requirement on the S matrix, on these elementary 2 to 2 S matrices, that they satisfy this Yang-Baxter relation. So this is a ubiquitous feature of integrable models in 1+1 dimensions. But this is just asking the scattering process to only care about the permutation and not about the particular way that the permutation is represented. Okay, so this is an ancient connection between the permutations on the one hand and particle scattering on the other. And if you're a red-blooded theoretical physicist and not an integrable models person, you would say, this is one of infinitely many things that's cool in 1+1 dimensions, okay? And has absolutely nothing to do with the real world, because obviously all sorts of cool things happen in 1+1 dimensions, as nothing can move anywhere, everything's got to bang into everything else. And also, there's no particle creation or destruction. This looks nothing like the real world where the fundamental interactions are 3-point interactions and not 4-point interactions. Well, that's what these new pictures that we're drawing are. These new pictures that we're drawing now do look like scattering processes that we care about in 3+1 dimensions. But they represent permutations in a different way. Not in this way where you put the stack of guys in the past and you evolve them into the future, but where you decorate the inside of the space-time with some, or you draw this kind of picture, right? Okay, so this is another way of associating permutations with pictures on the one hand, and they look like on-shell diagram scattering processes on the other. But you can ask a similar question. Here, the fundamental thing was breaking a permutation up into adjacent transpositions. What is the analog of adjacent transpositions in this world? Well, let's say I had, this is just a teaser for next time. Let's say I had some picture here, and here there's some index A, and the permutation sent it to some sigma of A. And here's A+1, and who knows what, and the permutation here sent it to some A+1. What would I have to do to, like, invert them? I have to put a white vertex here and a black vertex there. Okay. If this now sends this, you got to turn left. So you go through whoever A comes out, and here you go right, and you come through whoever A prime comes out on the other side. So what creates adjacent transpositions in this world of permutations is nothing other than the BCFW bridge. Okay. And so, in fact, we will give a canonical way of representing any permutation in this way by adding bridges, by starting from the trivial permutation and adding bridges. And of course, there's millions of ways of doing it, just like there's millions of ways of doing it here, but there's also simple canonical ways of doing it. So this old picture of particle scattering in 1+1 dimensions is associated with ordinary permutations. This new picture is associated with these planar diagrams, these Playpic graphs or on-shell graphs. The permutations are a little bit more interesting, as we'll talk about. We don't just care about whether one goes, we don't just care about the permutation. We care about how many permutations jump back, because these things are ordered around a circle. So that's why there are these decorated permutations, affine permutations, a lot of different words for it. And that's what the blacks and whites are letting us keep track of as well. So we'll have to be slightly more careful when we talk about how to build a general permutation out of these adjacent transpositions. We'll have to take care of whether things are jumping forward or back, and we have to be slightly careful about that. Even the notion of what the trivial permutation is a little more interesting, because when something goes to itself, you have to decide whether it goes to itself or it goes to itself plus n. Okay, because we have to care about whether it's sort of how it's going to itself, whether it's winding around once or just not doing anything at all. So that decoration is what the black and whites are about. And the entire rest of the story is some canonical way of associating permutations with pictures. And that way of associating permutations with pictures is literally BCFW. Okay? So really, literally BCFW. And after we get that all under our belts, we can start talking about positivity. OK, thanks a lot.